So we're finishing our lecture today on improper integrals. And the comparison tests. So just to warm up, we've done all of the techniques yesterday of substituting our dummy variables and taking limits to compute improper integrals. Sorry, let me move my notes around here so I can write. So just to warm up, let's finish the example we kind of left off with. We were doing the integral of 0 to 2 of x over x squared minus 5x plus 6 dx. And this is a type of integral that might appear on a quiz, exam, and may or may not look improper at the moment, right? Limits to infinity are a dead giveaway. It's an improper integral. I'm going to have to compute that limit out to infinity. With functions, though, you got to be careful. And of course, with a function like this, if you didn't know it was improper at the beginning, well, what would you do? Well, what type of techniques does this look like? You could try a U sub, which would work. The other thing you might try to do is partial fractions. Since we have this quadratic in the denominator, we know how to factor quadratics. It's a good thing to look for if you see a quadratic anywhere, especially in the denominator. We know how to factor those, so let's go ahead and try to factor it and see if it will factor. X squared minus 5x plus 6. So how's that going to factor? Well, it's a positive 6, and so we need factors of 6, 2, and 3. Of course, those will add to 5, and so we need x minus 2, x minus 3. And when we factor it, we see, well, now this function is going to blow up because I'll have a 0 in the denominator at 2. So there's going to be an asymptote at 2, and I have to integrate up to 2. So we know that this one is improper just because of that. So to deal with it, let's actually do a partial fractions technique first, and then determine whether or not we can compute this or if it'll diverge. So we've got a over x minus 2 plus b over x minus 3 equals, of course, x over x minus 2, x minus 3. I find a common fraction for the left side, and in the numerator, we will have x minus 3 quantity times a plus b times the quantity x minus 2. And that numerator should equal the numerator on the right. We can pick specific x values. So say if x equals 3, we will get b times 1 equals 3. So of course, b equals 3. If we check x equals 2, we will get a times negative 1 equals 2. And so a is negative 2. And so our integral now becomes integral of 0 to 2. Our a term was negative 2 over x minus 2 plus 3 over x minus 3 dx. So determining whether this integral converges is the same as determining whether this integral converges, and of course computing the values are the same. We can split this integral into 2 over the sum. And so for the sake of looking ahead a little bit and thinking about these comparisons, let's try to guess what's going to happen. So this guy here is fine. there's only an asymptote at 3. And since the bound, since we're integrating between 0 and 2, we're never crossing that asymptote. So it's fine. It's going to give me a finite number. That one we know we can do. Let's hold off on that one for a second, because this guy's the problem. If we identify a problem, if we identify that something is going to be divergent, there's no real sense in doing the rest of the problem. It's divergent. It's going to go off to infinity. We cannot compute it. It's going to be an infinite integral. So no need to do the work for that guy yet. Let's take a look at the problem integral. What's going to happen with that? What do you guys think? Converge or diverge? So you should start to get to a sense like, what's the power here, right? This is our power. Power is 1. It's an x minus 2, but that's just going to shift. We had this rule yesterday where a 1, something like 1 over x, or even a constant over x, what's happening with those integrals if they're improper? They diverge, almost always. Whether it's an integral to infinity or an integral around the asymptote, if the power is just 1, they diverge always. So if we tried to compute this guy, what do we get? We'll just get minus 2 natural log of x minus 2 of 0 to 2. And what's going to happen when I plug in the 2? We will get minus 2 natural log of 0 minus, and then now what's going to happen? Minus 2 natural log of, well, absolute value of negative 2. And so, of course, this guy is infinite. Can you guys see that? Am I writing still on the page? Yeah. And of course, we can't take the natural log of 0. It doesn't work. So it's going to be infinite. There's no sense in computing this guy then, because infinity plus some finite number is still going to be infinite. So it's a divergent integral. Any questions on that guy? Everyone writing notes, or anyone still writing?
I'm writing notes, but I needed the original problem.
Ah. So it's that guy there.
Sweet, thank you.
Yep. Okay, so let's talk about our comparison tests. And maybe before we do, let's get a list going of convergent integrals and divergent integrals. So, and let's compare and contrast them. If I have an integral, let's say between a to infinity of 1 over x to the p dx, this will converge if p is strictly bigger than 1. And of course, here we assume that our a is bigger than 0. So some constant bigger than 0, a positive number, so we're not crossing the asymptote. Integral out to infinity, as long as my p-value, I have a power bigger than 1, a quadratic, or even a fractional, x to the 3/2, going to converge. It will diverge if p is less than or equal to 1. And again, this is with our initial point bigger than 0. And then we saw that those two flipped if I need to integrate around this asymptote. So let's say 0 up to some point bigger than 0. If I have 1 over x to the p, it will only converge if my p now is less than 1. And it will diverge when my p is bigger or equal to 1. So, and these guys you should think of like rate of growth, right? What happens when I square a small number? If I have a number less than 1 and I square it, it gets even smaller. So if I have something like 1 over, 10, and if I have to square it or raise it to a power bigger than 10, it's going to make it even smaller. So any, power, any exponent bigger than 1 is going to make the denominator big enough so that the whole fraction gets small enough that it will converge, going out to infinity. So this is kind of like a rate of growth thing. Along those lines, well, what functions increase faster than a power function, faster than polynomials? These are, next natural one to talk about is our exponential functions. So things like e to the minus x, or in other words, 1 over e to the x. So really what we have is the denominator, our function in the denominator gets really big really fast. Gets bigger even than polynomials. So of course this will converge. Likewise, that's going to hold for any exponential base or any exponential function where the base is bigger than 1. Conversely, if a function grows slower than polynomials, it's not going to converge. It'll diverge. So integrals like a to infinity of 1 over natural log of x is going to diverge. And of course, all in these cases, our a was bigger than 0. Okay, so now let's kind of flip this a little bit. Instead of going out to infinity, what happens when I integrate around an asymptote? Things you kind of want to think a little bit backwards. Things almost go in reverse. Exponentials decrease really, really fast, right? This e to the minus x gets really low really fast. Whereas natural log, it grows really slow. So 1 divided by natural log is going to decay really slowly. But exponentials and natural logs are inverse functions of each other. So just as with power functions, what's the inverse, so to speak, of x squared? Well, we can't really find a true inverse, but if I wanted to, it would be something like square root of x. So the opposite kind of happens around the asymptotes that are created when we have those functions in the denominator. Does that make sense? So for example, like here I have my p less than 1, and of course these p's are always bigger than 0, because otherwise we could flip the numerator and denominator. When I have fractional exponents, these are like the inverse functions. They grow really, really slow compared to polynomials. However, around asymptotes, they get really, really tight. They get really, really tight around the asymptotes. So here, you can kind of think as the x-axis as my horizontal asymptote for this function, And this function will approach the horizontal axis really rapidly, and it'll converge. Conversely, if I take the inverse function, it essentially becomes a vertical asymptote around 0. And now when I take the inverse function, a fractional exponent, it'll approach that exponent or that asymptote very tightly, and it will converge as an integral. Similar things happen with natural logs. So while 1 over natural log is divergent out to infinity, if we integrate this around the asymptote, and I think we just want a natural log of x. That one should converge. And then I'm trying to think of what a divergent analog of that would be. Hang on. Let's check this guy real quick. I'm trying to think if I'm thinking natural log of x or 1 over natural log of x. So let's go through the example. We've got the integral from, 0 to a of natural log of x. I think we did this example yesterday. Let's check it one more time. So what was our antiderivative? It was x natural log of x minus x from 0 to a. Of course, remember we got that by integration by parts. When I plug in my upper bound, it's fine. My lower bound, though, what are we going to have to do? We want to compute the limit as t goes to 0 of essentially t natural log of t. When I plug in 0 for that x, fine. So it's not going to mess anything up. It's this guy here we got to take a look at. And remember how we computed this limit yesterday? We said natural log of t divided by 1 over t. And then we use L'Hopital's rule. Take the derivative of the numerator and denominator. We do the algebra. And of course, what do we get? The t's will cancel. And when we plug in the limit, we will just get 0. So we do get a finite convergent integral for this guy. Okay, so let's bring back up our comparison tests. I'm trying to think of any other ones. So let's keep this list as sort of a separate list. And then if we find any other functions that come up, maybe it'll be good to add them. So let's get at some examples and talk about, well, what are we doing with this comparison test? And we'll keep this, I'll keep this handy and I can bring it up on the video if you guys need to look at it again. Sorry, was anyone still writing on any of these?
My internet just went down, so I just got back up. Let's see, what did I miss? Nope, we're on the same page. Cool.
Cool. So let me keep that handy there. Okay, so what is our comparison test? So suppose we don't know if some integral which is improper and so the limits could possibly be infinity. We could have a as negative infinity or b positive infinity, or there could just be an asymptote or something going on with the function. Well, so if on the interval a to b, or of course if it's infinite, open brackets, we want to compare the functions. Suppose f of x is less than or equal to some other function. So I know that I can bound this function by another function, and I know that, well, this function, it's a little bit nicer. I'm able to just find a nicer function g of x that is bigger than f of x, and it converges. Well, then I know that the integral of f of x converges. So let me put sort of ellipses here, because this is sort of like our case one. So in some sense, like if I can bound this function by a bigger function, if something that is bigger than a finite, here, let me write it out. So we're comparing these two. If I know that the functions, since g of x is bigger, that means the integral has to be bigger. So think of it, if this has to be a finite number, then this has to be a finite number as well. Conversely, if we have a function that is smaller, on the end interval, and the smaller one diverges, then the bigger one has to diverge. Move that up a little bit. Right? Because we're comparing these two integrals. And if this one is infinite, then this guy has to be infinite because it's bigger than infinity. Those are the only two tests. Anything else is inconclusive. So be careful with that. And this is where the practice comes in. When you're first seeing this, you're gonna overthink things or think things in the wrong direction of logic. That's really the practice of this, is getting used to the logical implications of which one's bigger, which one's smaller, what is the result based off of that, and making sure you're getting the correct result based off of the correct comparison. So anything else is inconclusive. What do I mean by that? Well, let's suppose I have these two functions here, and I have, well, f of x is less than g of x. So we're going to have this integral is less than this integral. But if this guy goes off to infinity, can we say anything about this guy? No. All I know is that it's less than infinity. And infinity is one of those weird numbers where infinity is also less than infinity in some sense. This could still be infinity, but be less than this type of infinity. Or it could be a finite number. We can't tell. It's inconclusive. Likewise, in this case, if g of x is less than f of x, well, if g of x is finite, let's say this one converges, I can't tell anything about this guy. It could converge to a bigger number, or it could be infinite. It's inconclusive. We don't know. So the practice is trying to make sure you're setting up the correct comparison to use. And so just before we see an example, let's try to write down some tips. Let me see. Let me find my notes. Maybe we write it on this comparison test sheet. Let's do that just to keep our notes organized, just to have a sheet handy. So I'm going back to this comparison tests with the convergent and divergent list we had going. And then at the bottom, let's write a few tips. Let's leave some space just in case we want to add some extra functions, or you want to add extra functions for yourself as you're going through some of these examples or some of the homeworks you might come across. So tips. The biggest things that are going to come up are fractions. We've seen a lot of these rational functions so far, and with these improper integrals, rational functions are all over the place, right? Because we need functions to decay. So what functions decay out to infinity? It's either going to be like an exponential function or like 1 over something. Or it's an asymptotic function. It has an asymptote, which of course means there's going to be some sort of 0 in the denominator. So rational functions come up all over the place. So smaller numerator will make a smaller function. Conversely, you've got the denominator is different. Larger denominator smaller function. And of course, those flip when we change it. So larger numerator gives us a larger function. And a smaller denominator gives us a larger function as well. Other things that might come up, things we might have to consider in all of these. Consider size of numbers. And we also want to consider how addition and subtraction affects bigger or smaller. If I have an x plus 2 in the numerator, and I change that to just an x, that gives me a smaller value. Gets a little trickier when I have something like x squared minus x in the denominator. There's a subtraction there. So if I remove that subtraction and just compare it with 1 over x squared, is it going to make a bigger denominator or a smaller denominator? How is that going to affect the function? So those are things we're going to consider. The other thing we want to look out for, bounded functions. These come up a lot with trig functions, right? Sine and cosine are bounded between plus and minus 1. So I can usually just get rid of them in a comparison. When I want to compare something with a sine or a cosine in it, I can usually replace that with a plus or minus 1. We just got to make sure wherever that, if it's in the numerator or denominator, are we making it bigger or smaller based off of using the bound for a function. Let's see some examples of how this all plays out. Let me keep that sheet handy here, and I'll try to bring that up if we can touch on any of these points. Okay, let me find all the examples I've got. And if we get through these, see how much time we have. I think there were a couple on WebAssign that you guys got to do that. They can be a little tricky. So our first example is an integral from 0 to infinity of x over x cubed plus 1. So with rational functions, there's no sines, cosines, there's no exponentials or logs, just polynomials in a rational expression. You always want to compare the powers. What do we want to compare this to? If we look at our tests, this is kind of like the first example here. We're integrating out to infinity. Well, we got this 0 in the denominator as well. So we'll touch on that for a second. Let's look at the function first, then we'll consider the bounds and what's going on with those. Okay, well, just as a function, this is x over x cubed plus some extra stuff. And at least, well, now looking at the bound, since we are going out to infinity, at infinity, this plus 1, not going to matter much. This x cubed is going to get so big that plus 1 isn't going to change it. So this function is going to look mostly like one of these guys, something like 1 over x to the p. So we can kind of think of, well, which situation I'm in. I've got these divergent and convergent cases with all these 1 over x to the p's based on the power. So looking at it, if it's x over x cubed, it's going to behave, at least out in infinity, it's going to be like 1 over x squared. So I know I have a p bigger than 1. We just need to figure out, well, I've got an infinity, so I know I'm going to be here. Do we also need to consider what's going on at 0? And this is the one where it's a little tricky, because here we have a's, because sometimes the bounds could be different. So what's going on at 0 here? Is there an asymptote? Do we have to worry about this 0? It's not a problem, right? Because there's this plus 1, we don't have to worry about that 0 causing an improper integral at that end of the integral. It's only this infinity we have to worry about. Okay, but if I want to compare the integrals, so let's write some of this out. So we want to compare x over x cubed plus 1 with, here, let's make a little box. Well, if I just ignore that plus 1, we will have x over x cubed, and I know that that is equal to just 1 over x squared. So how are those going to compare? What did we do? We made the denominator smaller. So if I make a denominator smaller, what's going to happen? That means this guy, since it doesn't have a plus 1, it's a smaller denominator, so that guy is going to be bigger in general. However, we do have to worry about, well, what's going on with these small numbers? Because if this were a constant bigger than 0, this would hold. The problem is at 0, what's going on with this guy? This one's going to blow up to infinity. So it's going to get really, really big, and I can't actually compute that integral. So we've got to be careful, because this comparison while true, isn't quite the correct conclusion yet. Do I know that this guy converges? It actually diverges. And why is that? While the part going out to infinity, let's try to keep that all on screen if you guys can see it. The part going out to infinity is going to converge. However, the part at 0 is going to diverge. So we just got to be careful with this, something like this. And well, what can we do? Well, 0 wasn't an asymptote here, right? It wasn't a problem. What we can actually do is just write this as, let's pick a value. Let's pick our favorite number. Everyone likes the number 7, lucky number 7 here. Why 7? Because it's bigger than 0. That 0 is what's causing a problem here. And it's just kind of like a weird number that's screwing up our comparison, but it's not, it's just something we can work around pretty easily. So I've got 7 to infinity plus, keep my dx's in there, 0 to 7. So I kind of wrote them a little bit out of order because really it's this integral. I can integrate 0 to 7 and then 7 to infinity. But really, this guy here is finite. I know that one converges. There's no asymptotes, no infinities. I don't even have to consider this. So now if I change this a little bit and just say, well, now let's just consider this integral with this finite bound, this has to be true. Still true based on the size of the functions, but now changing that bound, what's going to happen? Well, now I'm in this case that we sort of first wrote. I have essentially a p-test is in some sense what this is called, and we'll call it that once we get the sequences in series. Since I have a power function, a polynomial, and the degree of the function is bigger than 1, and I'm integrating from a value that's non-zero. So I know that this guy here converges. So because this guy converges, then this guy converges. So let's write that out in a sentence, just because drawing arrows around isn't the best way to show your work. So since, sorry, we change that 7 to infinity of 1 over x squared converges. This integral converges. Our x over x cubed plus 1. And of course, since this guy was just finite, adding on a finite number to something that converges, which means it's a finite number, adding 2 finite numbers will give me a finite number. So we could say, hence, the integral from 0 to infinity of x over x cubed plus 1 converges. Any questions on this guy? Anyone still writing? Okay, so let's just get a new page. Let's take a look at that some more. So we've got integral of 1 to infinity of 2 plus e to the minus x over x dx. So this one we've got a rational function, but there's this exponential thing in the numerator. If I just look at that guy, this e to the minus x, and consider that e to the minus x out to infinity, what's going to happen based on our list we had going? That will converge. So this e to the minus x isn't going to cause many problems. It's this constant and this 1 over x. This constant over x isn't going to be a good thing for us. So what do you guys think? Any ideas? Convergent, divergent? If you're not sure, you can always do some algebra to start yourself off. So naturally what we should do, anytime I have a sum and a numerator, not a problem, right? Sums and numerators, we kind of like, they're easy to work with algebraically. So the natural thing to try if you have a sum in the numerator is to just split it up. So we've got 2 over x plus e to the minus x over x dx. And okay, I got my minus sign there. Well, I've got a sum now. We can split it up into 2 different integrals. Integral of 1 to infinity of 2 over x plus the integral of 1 to infinity of, you can write it as e to the minus x over x. Or if you want, you could write that as one divided by x e to the minus x, or e to the positive x there. So this one's not too bad. We kind of just had to do some algebraic manipulation to get started. And, well, how do we want to compare these two? What's going on with this guy? Convergent or divergent? This one will converge. So if you want to look at this guy, we had different formulations for it. We kind of wrote it as e to the minus x over x, same thing as 1 over x e to the x. You could also maybe write it like this, 1 over x times e to the minus x. Pay attention to your x values. This is something else that's going to come up, which we kind of saw when we wrote the examples. Integrating between an asymptote and a finite number is different from integrating from a finite number out to infinity. So always pay attention as to the size of the bounds that you're going to integrate. So since x is always bigger than 1, what happens if I have 1 over x? It's a smaller number. So this guy is going to be smaller than just e to the minus x. So since this function here is smaller than e to the minus x, this guy will converge. So this guy will converge. But what's going to happen with this guy? Here I know that, well, 2 over x is less than 1 over x. And I know that this guy diverges. Sorry, I wrote that backwards. You're going to make these mistakes as I just did. You'll write your comparisons backward. Your brain gets slipped, especially when you go from something that's convergent to divergent. We're comparing the wrong way. So my 1 over x is less than 2 over x. Right? Bigger numerator, bigger function. And this guy diverges. Alternatively, you can kind of think that the integral of 1 to infinity of 2 over x dx, this isn't using a comparison test. This is essentially just using the known fact that 1 over x dx, and this diverges off to infinity. And of course, 2 times infinity is still going to be infinity. And so our problem now is that because 1 to infinity of our original function, which is equal to 1 to this guy plus this guy, it will diverge. since this guy diverges. Is that all on the screen there? Oh, sorry, was it? So I was just writing sort of the closing sentence for this problem. So I just kind of rewrote the original problem, our initial step, and we kind of did our scratch work above. I know that this guy converges, but because this guy, the 2 over x diverges, the entire thing will end up diverging. Any questions there? Anyone writing?
I had a question concerning the divergence of 1 over x.
Yeah.
So I understand that it diverges, but I don't understand why.
What is, it's specifically, well, both, whether we're integrating from 0 to 1 or 1 out to infinity. So what's the antiderivative of 1 over x? Is natural log, right?
Mm-hmm.
And what happens when I plug in infinity to a natural log?
Okay. Yeah, that
Goes
makes
off
sense.
to infinity.
All right, thank you.
Yep. Okay, so we've got about 20 minutes. Let's try to go through some of these a little bit quicker and just try to get you the comparisons. Because on the exam, the way these type of questions are worked, these make really good multiple choice questions. Just because it'll be, we might give you like a function and say, well, which of the following conclusions is correct? And it'll say like, you know, the original integral will converge compared to this other function, or it will diverge compared to this other function. And so you kind of just need to be able to understand what we're comparing it to. Is it bigger or smaller? And then what conclusion do we draw off that? Will it converge or diverge? Let's see. Yeah, so here's a good one. This one has a little bit more going on. So it looks kind of like a polynomial, just a rational function, but we've got a square root that we got to be mindful of. And then we've got these sums and differences in the denominator and numerator. So you can always, you know, if you're doing your scratch work, let's pull out the function. We don't got to mind the integral when we're doing these comparisons. Though maybe it's good to kind of note the bounds. We are integrating from 1 to infinity. So if you pull up your sheet, we're going to be in one of those, we'll likely be wanting to use one of these types of tests. There's no exponentials, so I don't got to use any of these guys. And so we're going to likely be using something like this. The difference is we have a square root here. And remember, in these tests, the p's can be fractions, so these will still hold. So let's do some manipulations. My integral is from 1 to infinity. Well, I've got a 1 in the numerator. What happens if I make the numerator smaller? So let's just mess with the numerator first. If I make the numerator smaller, smaller function. So if I just get rid of that 1, what do I want? I'm just going to have an x in the numerator. And I know that that one was smaller, so I put it over here on the left. Okay. That's a nicer numerator. Let's play with the denominator now. We've got an x to the 4th minus x. It's all under a square root. How is the minus x affecting the denominator? My x values go from 1 to infinity. So the x values themselves that I'm going to plug in there are positive. And I'm going to be subtracting off positive numbers, which means this minus x is making the denominator smaller, right? Then if we want to get rid of that subtraction, if we want to just ignore this minus x, and this is kind of your common thought process, so I'm not sure if I've explained that, but really when you've got these polynomial functions, you really want to keep the highest powers and try to see if you can get rid of everything else. It doesn't always work, but most of the ones that we kind of cook up for these examples as a first pass before we get to sequences and series, we usually cook them up so that the numerators and denominators, the extra terms we're adding and subtracting, are kind of the right sizes, right things, right operations. So here, this minus x, if we wanted to get rid of it, I would have just an x to the fourth. And since this minus x is making the denominator smaller, a smaller denominator here means that this whole expression is bigger than this guy. Everyone follow that? So really, you know, take your time thinking through all these, make sure your functions are on the right side, your logical implications are all there. This function here has a smaller denominator, so that means this guy is bigger than this guy. So I'm kind of writing right to left with my implications there. So overall, what is our comparison? Well, I've just got x over now square root of x to the fourth, and that's nice. This is why we like to get rid of these extra sum and additions, because now I can take a square root of x to the fourth, and that's just equal to x over x squared. And our comparison was that this function is less than the original function. So that is the comparison we want to make. And of course, x over x squared is just 1 over x. So we have 1 to infinity of 1 over x dx. I know is less than our original integral. Sorry, I forgot that plus 1 there. So since this guy diverges, that guy diverges. So overall, I know that it's divergent. Questions, comments? Anyone writing? Okay, so let's maybe do one more and then we'll spend the last 15 minutes or so talking about this project. If you look on the schedule, we'll be practicing these a lot tomorrow. And it's good to practice. I wish we could have actual in-class meetings. It would be much easier for me to kind of get around and help you guys and check everyone's understanding. But the project for tomorrow will be important. It'll be good practice for all these. And so I'll be able to kind of jump around with the virtual groups and help you guys. Let's kind of just write out a few real quick and try to compare these. So we've got 0 to infinity, arctan x over 2 plus e to the x. And the more you practice these, you really just want to be able to look at the function and get an idea and just know convergent or divergent, kind of right off the bat. And then you should kind of work through and check yourself, you know, do the comparisons. You're not always going to be right with your first guess, but you should start to practice these enough where you get a feel for them. In this last one, for example, you should just be able to kind of see, well, if I just look at the highest powers, it's going to be x over, well, square root of x to the fourth is x squared. So you can kind of immediately see the x over x squared, 1 over x, and then get a sense that that should diverge. Then you just got to chase out the work to make sure you're correct. In this guy, what's happening? Well, what is arctan? What happens to arctan at infinity? I think we computed this limit yesterday. it's bounded, right? If you take tangent between minus pi over 2 and pi over 2 and turn it sideways, that gives you arctan. And so arctan is bounded. It's just going to be a finite number out to infinity. So really this function is just going to look like a constant divided by 2 plus e to the x. And e to the x is nice when it's in the denominator. It'll make things converge. So your comparison here should look something like this. So arctangent is less than pi over 2. And then if I make the denominator smaller, I get a bigger function. And I know that this guy will converge. So that this guy, if I compare it to it'll converge. Since that's just an integral of e to the minus x. And you can compute that integral if you wanted to and find the finite value. Of course, computing this integral and finding the finite value doesn't quite help us understand what this integral actually is. We don't know what value that's going to go to, and there's not nice techniques of integration to do that. But we know it will at least be finite. Let's see. Any other quick ones we want to just kind of mention? I think there's one similar to this one on the homework, maybe, on WebAssign. There's one with secant on WebAssign. So we've got secant squared over x square root x. It's just 0 to 1. And what's the power on the denominator? Something like x to the 3/2. So we've got secant squared of x over x square root of x. I know that that's equal to 1 over x squared of x cosine squared x. The reason I'm writing it to the left, what's my intuition here? My intuition is divergent. So I'm going to see if I can find a smaller function that will diverge. Why do I think it's divergent? Well, it's something like a constant maybe. If I could bound trig functions, we like to bound by constants. So think of this guy, I can bound it by a constant, and it's 1 over x to the 3/2. And by our comparison sheet, or our list, it's an integral from 0 to a constant, and my p-value is bigger than 1. So I'm kind of thinking of using this case here, that this guy is divergent. So my intuition is divergent. Let's see if we can get it to work out. Cosine squared, cosine is between -1 and 1. When I square those, it's between 0 and 1, which means that this denominator is bigger. If I just replace that cosine with just a 1, is what we did. 1 is bigger than cosine squared, which means this denominator is bigger. This whole function is smaller than this whole function. And so we get our comparison that we want. That it's an x to the 3/2. And so this one diverges. So that guy diverges. Similarly, last one, we've got 0 to pi of sine squared x over square root x. So just like in the last one, we've got a trig in there, but with these comparison tests, think of these trig functions especially sine and cosine at least, going to be constants that we bound them by. And so this should be something like 1 over x to the 1/2. It's x to the 1/2, but we're integrating around 0 around the asymptote. So what's our intuition? It's going to be this guy here. P is less than 1, and we're integrating around 0. So we should think convergent. Let's chase that out. Our sine squared x, of course, is bounded by 1. Now in the numerator, numerator is bigger, so this function's bigger. And that's really all we need for this guy. So we could say right integral converges. So the left integral converges. Any questions on any of those? Anyone still writing?
Yeah, I'm still writing.
Okay, I'll leave that up for a second. Let's see, we only got 10 minutes. Let's try to take 10 minutes. I don't know how much I'll be able to write. About this activity that we missed. You guys set or still writing?
I'm all good.
Cool. So let me move that out of the way. So let me try to bring up this stylus. And change the video. So this is our approximate integration activity. Look over this. I think the solutions are posted online on the website. So look over this, working it on your own. I'll keep you up to date as to how in depth the actual midterm is going to go over this material, because again, we didn't cover it in a lecture or anything. It's just this activity. So there's going to be at most one question like this on there. So really what's going on, everyone's familiar with the right and left hand Riemann sums. We just want to introduce some of these other rules where instead of right hand and left hand, we could pick really the midpoint of the interval and use that as my height. Or we could be even fancier and try to get a tighter approximation by making trapezoids out of them. So just like with the right hand and left hand sums, all we really do is use the geometry of, well, a rectangle and add up, you know, the sum of all the values of those rectangles, sum of all the areas. Same thing with the other two. Of course, midpoint, you still get rectangles. And in the trapezoid rule, you just got to remember how to find the area of a trapezoid. The area of a trapezoid is the average of the two sides, the two bases, so to speak, the two parallel sides, times the height. So in this case, they're kind of sideways. It's really the average of the two heights and then times the width. So in all of these, you have this delta x. That's where the width comes from. And then you taking the average. That's where that 1/2 essentially comes from. So really what happens with the trapezoid rule is that it's just the average of the left-hand and right-hand sums. Then there's this fancier one here on Simpson's rule, where instead you approximate each height by a parabola, and it's really technical and really complicated to, not really give you much more information. And here's a fancy formula for it. So it's just this guy. So if you're familiar with these formulas and comfortable with plugging in formulas, that's all you really need to know. I don't even know if Simpson rule would ever be asked on a midterm because it's really complicated. It's hard to teach. We're not going to be able to derive it. The midpoint and trapezoid rules are kind of the ones you want to pay attention to. So let's take a look at this guy. Let's change my color. What color you guys want? Let's do blue. So left-hand and right-hand sums. So we've got a table. We've got 7 values. So count them 1, 2, 3, 4, 5, 6, 7. We're integrating between 5 to 17. You just got to remember, how do I do the left-hand integrals and how do I do the right-hand integrals? And then, of course, pay attention to the partition size. So with 3, n equals 3, we want to use this guy. So we're starting, left-hand just means we're starting on the leftmost value. And then since I'm only taking 3, we want these 3. So those are going to be my values. Of course, we want the heights. You would just add up all the heights. My delta x in this case is 4. And then you would have -2 plus 1 plus 4. For that guy. Unfortunately, I don't think I can erase these. For n equals 6 with the right-hand sum. So of course, the reason why we need 7 is the spaces between there. 5 to 7 is one space, 7 to 9 is another space. There's 6 spaces. We just got to use whichever endpoint on the spaces. So with the right-hand sum, we would want to use all the values, at least the right 6 values. How do I do the trapezoid and midpoints? So those are what's going to be new. So let me erase all this. The trapezoid, what you would probably want to do is just take the average of the left-hand and right-hand sums. Might be the easiest, or of course you could essentially just follow the formula and compute it. But if you compute the left and right-hand sums, average the 2, that gives you your trapezoid rule here. Which you guys should be pretty comfortable with doing from a table. The midpoints are a little tricky because the midpoints, you have to create a different table because we cut it up 5, 7, 9, 11. Our delta x is 2. But if I want to use the midpoint rule for a partition of 6, well, the midpoints lie in the middle of the values. So here we have like our 5, 7, 9. Those are the values we have listed on those tick marks. So this would be our 5, our 7, our 9. But the values of the function we need are in between there. So we can't actually compute that guy. Oops, let's see, undo that. So this guy, can't compute. We need, so what would we need? Well, if our first interval is between 5 and 7, I need the midpoint of that. So I need 6. And I need the value of the function at 6. Then we would need the next one. We would need f of 6, f of 8, f of 10, etc. They change it up then and say, well, let's compute the midpoint now for n equals 3. This one we can compute. So if n equals 3, here's our 3 partitions. And the partitions are the space, right? Between 5 to 9 is one space, one box. The height's going up. 9 to 13 would be the next. 13 to 17 would be the next one after that. So if we want the midpoint of those, so if my first interval is 5 to 9, the midpoint is then 7. The midpoint between 9 and 13 is 11. Midpoint between 13 and 17 is 15. So those are the values we want to use. The width of the interval, 5 to 9 is 4. Again, 9 to 13 is 4. And likewise for the last one. So my delta x is 4. The values we want are the values that we circled here of the function. So it would just be 4 times, what do we got? 0 plus 3 plus 5. Does everyone see that? So how does that fit in the function? My delta x was 4, then this would have been 0 plus 3, or the height would be 0 plus 3 plus 5 for the next one. Any questions on that? Sorry, I think I'm a minute over. I don't want to keep you guys too long. We'll do the activity tomorrow on these comparison tests. Look over this guy. Try to get a feel for at least some of these guys. And I would say, especially on some of these last ones, the solutions are posted on Canvas. So just look over of when we get overestimates and underestimates. You guys should know that for your left and right hand limits, but you'll be able to figure it out as well for the trapezoid rule and the midpoint rule. And then get a comparison of essentially which one's biggest, which one's smallest based on the shape of a function. All right, so that's it. I'll go ahead and stop the lecture. Stick around if you got any more questions.